Welcome to section 11.4, limits at infinity and limits of sequences. So we just finished up sequence and series, and so now we're going to jump back into the limit side of things. Couple of things. First, I want you to actually just go ahead and see if you can evaluate this function as the limit of x approaches infinity. So just pause the video for just a second, go ahead, plug that into your calculator, whatever you need to do, and see if you can find the limit as x approaches infinity. Alright, so as you hopefully came up to maybe some conclusion as to what this might be, I've graphed this in the calculator, and as x gets really big, I keep zooming out here, we're at 100, and where is it going? Well, and I keep going, I'm already at 1,000, and what's happening here? So it looks like it's getting closer and closer to maybe the value of 0 possibly. Alright. How are we supposed to know for sure though? Well, let's go ahead and go to our table. And you can see, let's see if I do my table set here. I want x to get really large. And let's see where it's at now. So you can see I'm up in the 293,000 or so, and so it doesn't maybe actually get closer to 0. Maybe it gets closer to this value of 0.5. It looks like that's where we're going in this case. Whoops. So how do we know? Well, as we look at this, the limit as x approaches infinity is 1/2 or 0.5. Why is that? Well, what is happening on this rational function here? Well, we talked about as x goes to infinity, we've talked about in behavior before. And we've also talked about horizontal asymptotes. And that's exactly what this is. Remember the degrees of the numerator and the denominator when they're the same? You take the leading coefficients, and that gives you the horizontal asymptote. Well, if the horizontal asymptote is at y equals 1/2, then think about that. As x gets really big, what is it getting closer and closer and closer to? The value of 1/2. So limits at infinity, we're looking for the horizontal asymptote. Where is it approaching? So as you look at these next couple examples here, it says find the limit as x approaches infinity of negative 2x plus 3 over 3x squared plus 1. Well, now we know as x approaches infinity, what is happening with the horizontal asymptote? Well, we got to go back and look at our degrees. So the degree on top is 1, the degree on bottom is 2. What happens when the degree on top is 1 smaller than the degree on bottom? The horizontal asymptote is at y equals 0, so therefore the limit is approaching 0. And once again, if you have a horizontal asymptote right here, then the graph is going to approach that as it gets really large. You've got to make sure you pay attention to these values. What is it that you're asking? So on B, you have same degrees, degree 2. So you look at your leading coefficients, and the horizontal asymptote is at negative 2/3, so therefore the limit is at negative 2/3. Alright, and then on this one, this last one, you have the degree is larger on top than it is on bottom, so we don't have a horizontal asymptote. Well, if we don't have a horizontal asymptote, then as x gets really large, okay, we can graph this and find out, but it's going to be shooting off to infinity of some sort. So as x gets really big, what's going on? Well, it's going to infinity, so this one does not exist. Okay, so it doesn't exist because the limit approaches infinity. And there you go. So we now know that limits of infinity really just have to do with your horizontal asymptotes. And so we've got to pay attention as to what's going on in the graph and what that horizontal asymptote is. So here's 3 more questions real quickly. Why don't you go ahead and just pause the video real quick, answer these questions, and then we'll move on. So the first one, look at your degree. You had to multiply to get a degree of 2 on top and a degree of 1 on bottom. So once again, it's going to shoot off to infinity, so it does not exist because the limit approaches infinity. On the next one, the degree on top is smaller than the degree on bottom, so the horizontal asymptote is at 0, so that one's, the limit is 0. And then the last one, the degrees are the same, so you take -6 divided by 3 to get -2. So that's really it. I mean, in terms of limits at infinity, that's really what we're going to be focusing on, is that horizontal asymptote. Once again, pay attention because that's only true when you're looking at infinity. We're going to go back to that idea of a sequence. So we're going to look at the limit of a sequence. So here's a sequence, a sub n is equal to 1 over 2 raised to the n power. So we're going to find the limit as n approaches infinity. So we're still kind of looking at those limits of infinity. And what's going to happen here? Well, let's just kind of plug in some numbers and see what this sequence looks like. So if we plug in n equals 1, that's 1 over 2. Plug in n equals 2, that's 1 over 4. N equals 3, that's 1 over 8. N equals 4, and we're just 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and so on. You can see the bottom number doubling every time there. So what's the limit then? What's going on as this sequence continues? What does it look like it's approaching? So as n gets really large, what's going on? It's getting 1 over a really large number, so it's getting closer and closer to 0. When this happens, the sequence is said to converge. It's converging to something. So as n increases without bound, we're talking about infinity, the terms of the sequence get closer and closer to 0. Now, this is talking about this particular example. So the sequence can get closer and closer to a different number, but it's that limit that we're looking at. Okay? So as it increases without bound, which means going to infinity, it's going to converge. It's going to get closer and closer to that value of 0, which sounds exactly like a limit. Okay? So here's another example. The limit as n approaches infinity as -1 is raised to the n power. Well, think about this one. What happens on this one? Well, -1 to the first power is -1. -1 to the second power is 1. -1 to the third power is -1. -1 to the fourth power is 1. -1 to the fifth power is -1. And it just keeps going back and forth like that. So what's happening here? Well, nothing. It's not converging to anything. It's just jumping back and forth. So the limit on this one does not exist. And it doesn't exist because the sequence does not converge, it diverges. Okay, it doesn't approach anything. Okay, in this case it's just jumping back and forth between 1 and -1. So when we look at these sequences, from what we talked about the other day, I want to have you do a couple different things here. First, I want you to list the first 5 elements of the sequence. Once we do that, we're going to figure out whether it converges or diverges, and then we're going to find the limit if it does exist. So those three things are what we're going to be looking at. So to find the first three elements, as n approaches infinity, we want to find when n is equal to 1 all the way up to n is equal to 5. So you're going to plug these into your calculator and figure out what they are. So if I plug in n equals 1, this would be 2 times 1 plus 1, 1 plus 4. So that would be 3 over 5. So that would be the first term in the sequence. And then we'll just keep doing this. Plug in 2. Got 5, 6. Plug in 3. You'll get 7 over 7, which is 1. Plug in 4. You get 9/8, and plug in 5, and you get 11/9. Now, if you're just looking at these numbers and you're trying to figure out where's this going, well, remember, this is only the first 5 terms in the sequence, and we're trying to go all the way to infinity. So is really the first 5 terms or 5 elements of the sequence going to determine whether we know if it's converging or diverging? No, we're not going to know. We need to look at numbers a lot larger than this, not just the first 5. We want to know what's happening at n equals 100, n equals 1,000. As n gets closer and closer to infinity. Well, if you actually look at this, once again, this goes right back to limits of infinity. Even though these are sequences, we still are looking at rational functions. And so when you look at the degree of the numerator and the denominator, they're both 1. So as we look at this, these are the first 5 terms. The horizontal asymptote is happening at y equals 2, so it does converge, and it converges at 2. And so that's the limit. As n goes to infinity, it gets closer and closer to that value of 2. Okay, so even though they're sequences, we're still really looking at those limits at infinity. So we're looking at those horizontal asymptotes again. So first 5 elements of the next sequence, if you plug them in, you can pause and try it on your own, but you got 2/5, 1/2, 6/13, 8/20, which would reduce to 2/5, and then 10/29 is what I got. So those are the first 5. Once again, we don't know what's going on here. It's really hard to see as to where this is going. Once again, this is only the first 5 elements of a sequence that goes on forever. So we look for that horizontal asymptote again, and you can see the degree on top is 1 larger. So we know it does converge because we do have a horizontal asymptote at y equals 0, which means the limit is getting closer and closer to 0 as n increases without bound. And then the last one on C, once again starting at n equals 1, we plug in 1 and we get 1/2. 2 over 4 reduces to 1/2. On the next one, if we plug in 2, we're going to get 5/16, it looks like. On the next one, if we plug in 3, we get 10/36, which could be reduced by 2, so that'd be what, 5/18. And on the next one, I think we get 17/64. And then the last one, if we plug in 5, we'll get 26/100, which can be reduced to 13/50. Once again, that's the first 5 terms, but what is happening? Well, the degrees are the same, so we take the leading coefficients, and once again, this one does converge. And as it approaches that horizontal asymptote, it approaches it at 1/4. It gets closer and closer and closer and closer to that value. Alright, so that's a sequence. That's limits of sequences and also limits at infinity. You can see that they both are very similar because we're still looking at really limits at infinity for both parts. Whoops. trying to go back to there it is. Evaluating limits of functions at infinity. And that's what we're doing throughout. Even limits of sequences, we're looking at infinity here. So, alright, I have one more question for you I want you to try on your own. And so take a look at this. I want you to find the limit of the sequence whose nth term is. So we have a sub n, and I want you to find the limit of this. So we're looking at the limit as n approaches infinity of a sub n. So you don't have to tell me the first 5 terms of the sequence. I just want you to find the limit. Okay? So pause and see if you can figure out how you're going to do that of this sequence. A little bit messier than the other ones, but still the same idea. Alright, so I'm just kind of working through this as you guys work as well. So the limit as n approaches infinity of a sub n. I simplified it and I got this. So I was simplifying the whole thing because, once again, as n goes to infinity, we're looking for the asymptotes, which means we're looking for, okay, what are the degrees of the numerator and denominator? So I simplified all the way down. The degrees are both 3, so I know that the limit as n approaches infinity of a sub n is 16 over 6, which reduces to 8/3. And so that is the limit as that approaches that. Now remember, even though we're doing sequences, you can still plug these into your calculator. As n gets really large, you'll just have to put in a really large value as you see that. So that's kind of more to help you check them. But as a reminder, you can do that as well, as to kind of look. But I still want you to look at these algebraically as what is that horizontal asymptote. So you guys have bookwork for today. And that is it. Thank you.